Hello everyone, welcome to another video tutorial of the course. In this video, I am going to present a simple example to learn how to use EMDLAB to solve a magnetostatic problem. So the aim is to learn how to generate the geometry, how to generate the mesh, define the solver, apply the boundary conditions, and solve the problem and visualize the data. Okay, so yes, this is just an example to learn scripting for EMD lab. Here, let's generate a new folder for our course, Advanced SPMSM Design, and navigate the MATLAB current folder to this folder that we created, this one. Okay, so here create a new M file and let's initialize it. Initialization. Clear the command window and clear the previous variables that we defined. Close all existing figures, and then we need to add the EMDLAB files right to the MATLAB path. I explained the installation process of the EMDLAB in another video. Its link is available in the description of this video, so you can watch that video, how to download the last version of the EMDLAB from GitHub and install it on your computer. So add EMDLAB to pass. We need to use this one, generate path. This is the EMDLAB path is in C, EMDLAB Win64. So when we generate full path, we need to add it. This is the first line that we need to create here, and this is just an example. Let's save our M file here. So as you know, the first step for the finite element modeling is creation of the geometry. In our case, we have a two-dimensional geometry. Then we need to create the mesh, in our case, a triangular mesh. Then we need to define the solver, solve, and finally post process the data. So here we have a 2D geometry modeler in EMDLAB. However, if you already have a mesh, directly you can pass it to the mesh database of EMDLAB and then define the solver. So EMDLAB has a built-in geometry editor, but if you have mesh and generated the mesh with softwares, for example, Gmesh or MATLAB PDE tool or any app that you used to generate a triangular mesh, you can directly pass it to the mesh. I will explain it later. So the first step is to create the geometry, a 2D geometry. I am going to consider this simple and basic example. We have the analytic solution for it. So consider a round wire in free air. I am going to calculate the field, magnetic field around this wire. So the direction of the current is out of the paper. And as you know, we have this magnetic field around this wire. So we know the exact solution, okay, in this case. As you know, if we consider this as the radius of the wire r, so we can use the ampere law, integral of h dot dl, right, is equal to the current that is inside the enclosed surface, and finally calculate the value of the h. And as you know, if I consider this x-axis and this as the y, so this is the by along the x. You know the analytic solution is simple electromagnetic problem. So as you know, if I want to plot the by as a function of x component, we have rise in the value of the by linearly, and then we have something like this, right? Because the integral of h dot dl is ni when the value of the r is higher than the radius of the conductor. Let's call this rc, radius of the conductor. So we know that this integral is h times 2 pi x. X is a variable from the origin up to here, the radius, that we are going to calculate the field intensity. This is equal to the I. This capital I is the total current, and in our case is equal to 1. So H is equal to I divided by 2 times pi times x, and B is equal to mu 0 times H. So when x is equal to RC, also we can calculate the value of the B. So here are variables that I am going to define. Our inputs are RC. Let's consider it equal to 5 millimeter. This is the radius of conductor, and RE, this is the radius of the enclosure. We need to consider enclosure around this wire to calculate the field, right, and apply the boundary condition. I consider it 10 times higher than the radius of the conductor. So this is the radius of an enclosure, the unit millimeter, and the unit is also millimeter. Also, we need to consider the total current. I consider it equal to 10 kilo amps, right? Total current passing through conductor. So now we need to generate the geometry. Here is the comment creation of geometry. To define geometry, we need to use elementary objects such as points, edges. Edges can be segment, arc, spline, right? And any type of edges. Then using edges, we define loops. Then we define faces. And after that, we can generate the mesh. So I can create geometry using this method first. Then I explain a simpler one. Here, first, I need to get an instance of EMDLAB G to the database, and then I can define my geometrical entities. So let's run the M file. Now we have G here, the geometry database, and now let's add the points. So G dot add point. I add a point at the center, 0 and 0. Then G dot add point at radius of the conductor and 0, and add a point at negative of radius of the conductor and 0. Then G dot show a sketch to check the points that we defined. So if I run the M file, here you can see we have defined P1, P2, and P3. So now using these 3 points, I can draw an arc from P2 to P3 and then from P3 to P2. So here I can use this method G dot add arc. So to define an arc, we need two indices of this point. The index of the first point is P1. This point is 1. The index of this point is 2 and 3. This function has two outputs: the index of the point and the handle, right? A handle to the point object. I will explain how we can use handles, and also this is an efficient method, and we have direct access to geometrical entities. So this is really good for shape optimization. So here, this is P1 index. I don't need to get the second output, the handle. So just I get the index of the first point, the second point, and the third one. So I can define arc using P1 index, P2, and P3. So here, as you can see, this function gets 4 inputs. This is the index of the center point, a start point, and end point. Also, we need to specify the direction. Okay. As you know, when we have 3 points, 1, 2, and 3, to define arc, there are 2 possibilities. We can consider this arc or this arc, right? So the direction that we move from the point number 2 to point number 3, it can be counterclockwise or clockwise. So we need to specify the direction here. I set the direction equal to 1. This is counterclockwise. So if I run this code, let me check. Yes, we have added this arc, and this is the edge 1. This is P3. Excuse me. Yes, this is the arc that we created. By default, the number of arc points is equal to 5, right? But if you want to visualize this sketch better, you can set the mesh size, the wireframe mesh size. So set mesh max length, for example, equal to 1. And let's rerun the code. Here you can see the arc that we defined. So now I can define another arc. Let's copy this, paste another arc from P3 to P2, run. So this is E1 and this is E2. We have added two edges. So also you can consider the direction of this edge. Okay, so we have directed edges in the geometry database of the EMDLAB. Here you can see the edge that we defined. This is the direction of the first arc and direction of the second one. So now using these two arcs, we can define a closed loop. Okay, we can define a closed loop. So this loop is counterclockwise. The correct direction of the loops that we define in EMDLAB are counterclockwise. And using a loop, we can define a phase. So here, the output of these functions is also the index of the first edge, and this is index of the second edge. So now using these two edge, I define a loop g dot add loop. This loop is using E1, the first edge, and the second edge. So this is L1 index. Using this function, we define a loop, and this function returns the index of the defined loop. Consider that all loops must be counterclockwise, otherwise you get error, and this should be properly ordered, right? E1 and then E2. So if you defined E1 in this direction, because in this case the direction of the edge is in opposite direction of the loop, you need to consider a negative sign here. So later we will use it when we are creating the geometry of the motor. So finally, when we have the loop index, I can define my base. So this is the conductor. You should specify a name and indices of loops that you are using to build up this phase. As you know, in general, for a 2D phase, if this is a 2D phase, we can have one outer loop and multiple inner loops. So this is L1, L2, L3, If you have holes inside the face, you can define them like this: L1, L2, and so on. So if I run this M file and then write g dot show faces, as you can see, only we have defined this face. So we can continue and also define the enclosure. But the question is, do we need to create a geometry like this? We can use the EMDLAB templates to generate the geometries faster. Even you can generate your templates. So instead of writing this code, simply I can write here g dot add circle loop. The center is 0, 0. The radius is RC. This is the loop 1. And the second loop is the RE, the enclosure. So the conductor is constructed by the first loop, but the enclosure, the air, is constructed by the second loop as the outer loop and L1 as the inner loop. So if I run the code, here you can see the sketch, right, is defined using these two functions, and I can write g dot show faces. So here, as you can see, we have two faces. We have a conductor and air. So here is the L1 index. So let me check g dot show faces. This is face 1 and this is the phase 2, right? We have two phases, phase 1 and phase 2. So that's all. We created the geometry of our problem. This function is important because it specifies the wireframe mesh. This is the wireframe mesh that we have. And in this case, we used equally spaced points, right, for this wireframe mesh. And in this case, our mesh will be uniform. Actually, the 2D mesh is controlled by this wireframe mesh, the size of the wireframe mesh that we have here. That is the next step, mesh generation. I define the mesh variable here, g dot generate mesh. We can specify the mesh generator here. If I don't specify anything, by default, minimal mesh generator is selected. So m dot show mesh zones. Let's try this m file. As you can see, the EMDLAB uses a minimal mesh generator to generate the mesh. This is not good, right? It just considers the wireframe points to generate this mesh. But we have other mesh generators. For example, MG0. If I run the code, it takes more time to generate the mesh, but here in this case, we have a good uniform mesh, right? This is the conductor and this is the enclosure. But we know that for our problem, this dense mesh is not needed. We can use um, non-uniform mesh. So how we can control the mesh size? Instead of using this method, I write this g dot set loop mesh max length. So set the mesh size for the first loop equal to 1 millimeter, and for the second loop consider equal to 5, for example. So let's try the code now. Here we created the mesh faster and this mesh is better. So here we have a uniform mesh for the conductor, but we increase the size of the mesh size as we approach the boundary of the problem. So yes, this is good. And here you can see we have access to all low level functions and we can handle or modify them in EMDLAB. EMDLAB is open source. Even you can modify these functions, right, to make it very good and compatible with your design. So let me delete this one. I don't want to show a sketch again and again. So what is the next step? We created the mesh. We need to add materials and assign materials to each mesh zone. Here, as you can see, we have two mesh zones. We have conductor and this air. Here you can write m dot mesh zones, and as you can see, we have two mesh zones, the conductor and air. And if I write m dot mesh zones dot conductor, as you can see, by default the material is set to air. Okay, but also you can change the material. Here I can write m dot add the material. I want to add material to this mesh database. You need to select the material name. So this is copper, and I need to pick up a material object from the mesh database. So EMDLAB material library copper. I add this material and m dot set material of this mesh zone, the conductor. I want to set material to copper. So this is a material object in EMDLAB. If you run it here, you can see the properties of the copper. Even you can modify the properties, okay, or define a new material that you have. So I added this material to the mesh database and assigned it to the conductor, and the material of the air is by default the air. We don't need to add that. So yes, we generated the mesh and we assigned proper materials to mesh zones. So generate mesh and assign materials. Okay. The next step is to define the solver. I am going to solve a magnetostatic problem. So here I define the solver, define solver S is equal to EMDLAB solvers magnetic static 2D TL3. Our problem is isotropic homogeneous, but it can be nonlinear. However, in this example, I didn't use nonlinear materials with nonlinear BH curves. So this solver uses 3 points, triangular Lagrangian elements to solve the problem. The input is the mesh. So let me run the M file. Here, as you can see, we have defined the solver correct. As you can see, mesh generation is instant. And when I run the M file, right, we can generate the mesh in a very short time. So s dot set length unit. The length unit that I'm going to consider is millimeter. Our dimensions are in millimeter. Then we need to define the excitation. So I define excitation. Here I can just define a simple coil. S dot define coil 1, and S dot add mesh zone to coil. So coil 1, which mesh zone we are going to add? We are going to add this mesh zone to the defined coil. And here also we have some inputs. The number of turns is 1, the direction 1, the fill factor is default, right? I set it equal to 1. So the direction of the current is out of the paper, 1 turn. So let me run the code. Here I can write s dot show all coil arms. Here, as you can see, we have defined this mesh zone as a coil arm. And if I write s dot show coil 1, yes, you can see this coil arm. The direction of the current is out of the paper, so the color is blue. If it is inside the paper, the color is red. So here, if I consider the direction -1, as you can see, this is red. But in our case, we consider the direction of the current out of the paper. Yes. So now we need to specify the boundary conditions. So boundary condition. How to specify the boundary condition? Here, if I write m dot show m, you can see the global mesh. All the problem, and solver will solve the problem considering this initial mesh. So here we have 2 mesh zones, and if I run this m dot show free boundary, you can see the free boundary of the problem. We need to specify boundary conditions on this free boundary. Or I can write m dot show nodes m dot get free boundary node. So this function gets the indices of the boundary points. So if I run this, here you can see the boundary points. So how to specify the boundary condition? Simply, I can use this function and s dot set az magnetic vector potential boundary condition. Set the value of the magnetic vector potential for these points, these boundary points. You need to specify index of the point equal to 0. That's all. We specified the boundary condition. Finally, we can solve the problem and visualize the data. So here s dot solve, and finally we can run s dot plot Bmag F, Bmag and flux lines. So if I run the code here, as you can see, yes, I forgot to define the value of the current. Define, excuse me, set coil current. The value of the current for this coil is equal to I. So if I run the code, here you can see the solution, the value of the field and flux lines. So let's change the color bar range is high now for our problem. We can set the limits here. If I write 0.4, yes, you can see the value of the magnetic field, the amplitude. We have the maximum value of the magnetic field, the magnetic flux density, right here, when the radius is equal to RC. And here also in this image, you can see this case. Also here, when you generate this plot, you can set the limit using this function. Limit from 0 to 0.4, the color bar limit. Consider that this function is available in this version or later. So in the previous versions of the MATLAB, this function is not available. If I run the code, here you can see the solution of the problem. We solved this classic problem, and now I am going to plot this graph, the value of by versus x. So I am going to check, can I draw this function or not? Here I define sample points xi, line space from 0 to re, consider 1000 points, and yi is equal to zeros, 1 and 1000 points. So bx and by, I'm going to use this function, this method from the solver, s dot get bx by on points. I want to get the value of bx and by on points xi and yi. So I specified these points, and I'm going to get the value of bx and by. So yes, now let's plot xi and by. Plot this graph. As you can see, yes, here we have increase in the value of the magnetic field, the by component, and here we have this pattern, right? This function. The maximum occurs at the conductor surface. The maximum is equal to, let's check, is equal to I divided by 2 times pi times r conductor times 1e minus 3, because this is in millimeter, we need to change it to meter. So this is h times mu 0, the permeability of the air, that is 4 times pi times 1e minus 7 times I. As you can see, the peak value is equal to 0.4. Okay, so here you can see this pattern. But why we have something like this? Here the reason is we used first order solver. And for the first order solver, the value of B is constant inside each mesh element. Okay. So to calculate this graph with a better and better precision, you need to reduce the mesh size. For example, here if I consider it equal to 0.5, yes, here let's plot the mesh zones. Here we have a more dense mesh, and this is the curve, the solution. But also, you can use the second order solver that is more accurate, and even with this mesh, you can generate correct results. So if I use TL6, the second order mesh elements, in the current version, if I write m.show mesh degree, you can see the degree of each mesh element. We are using 3 mesh nodes per element. But in this case, if I run the code, as you can see, we have this nice solution, because in this case, we used second order mesh elements. And here, if I write m.show mesh d, as you can see, for each mesh element, we have 6 mesh points. For nonlinear problems, if you are going to calculate motor parameters and do the simulations fast, you can use the first order elements. But for more accurate results, you can use the second order one. I will explain it and how we can use the first order good for our design. Both are available in EMDLAB. So yes, here also let me explain other functions that are available. Here you can write m.plot bmag. This is one of them without flux lines. Again, I need to specify the limits of the color bar. Okay. Or s.plot flux lines. These are flux lines. And s.plot bvec on central elements. You can check the b vectors on central each mesh element, the flux density vectors. But if you want to see all results in one figure, you can write s.gui, and here we have the problem and mesh and the solutions. So this is the mesh, the wireframe, free boundary, mesh information. The total number of elements is 2200. And here we have defined one coil. This is the amount of the flux linkage, the boundary condition that we defined. And here are field plots. Here you can change the range again. Here are flux density and flux vectors and other solutions that we have. Here you can even change the color map properties, the color map properties, the limits, and the color map type, right? You can generate good graphs for your report. Anyway, in this video, my aim was to explain this simple problem. We have an analytic solution. We can compare the data. And I explained this workflow, how we can solve a simple magnetostatic problem in EMDLAB. In the next video, we will consider the geometry of the motor, and we will do this process considering the motor geometry and continue the design. Thanks for watching.